Hello, in this video, let's discuss a little bit about ratioed gates and dynamic gates. So we look at some additional circuit families that were in the vogue in the 2000s, especially when people were trying to squeeze the fastest speeds out of processors. However, what turned out is many of these circuits turned out to be consuming a large amount of dynamic power and were not robust enough. So they have fallen out of use recently, but it's a good idea to know them because they do find use in some niche applications today. So let's first look at a class of circuits known as ratioed circuits. So these are drawn from pseudo-NMOS circuits, and what we do is instead of using an active PMOS network, we use a PMOS load to pull the output node high. So for example, an inverter in this technology would look something like this. If you look at this PMOS, the PMOS gate is connected to 0, which means this PMOS is always on. So when I want to pull the output low, I need to ensure that this NMOS is able to overpower this PMOS and eventually pull this output low, right? So in that case, what's going to happen is that you're going to see that when A is 1, that is when this NMOS switch is turned on, there is going to be a continuous current that flows from VDD to ground. So this circuit is going to consume power even when the input is not switching. And so when we select the size of the PMOS, we're going to select the PMOS as a compromise between noise margin and speed. So let's look at an example. So in this case, I want to design a ratioed inverter, right? So I want to design an inverter in such a way that when the output has to be pulled up, there's no issue, it's going to be pulled up slowly through the PMOS. But when the output has to be pulled down, the NMOS has to overpower the PMOS charging of the output capacitor. So here we're choosing a PMOS whose drive strength is roughly 1/4 the size of the NMOS. So here if you look at the NMOS resistance, the NMOS resistance is 3/4 and the PMOS resistance here is going to be 1/4 that of the NMOS. So when the output is being pulled down, right, let's assume that a current I was being pulled in the smallest inverter. So if I think about the smallest CMOS inverter in this technology, let's say it has a current I during pull up and pull down. Now if you look at this circuit, in this CMOS, the NMOS had a size of 1, so it was flowing a current I. Here now the NMOS has a size of 4/3, so it's going to pull a current of 4I/3 across the NMOS. The PMOS, however, because it's always on, is going to push an I/3 current from the supply towards the output node. So if I think about the capacitor which is sitting at the output node, the net discharge current of this capacitor is going to be 4I/3 minus I/3, which is I, in which case it's going to be as the same current that would have flown in a static CMOS inverter of size 2/1, right? So this circuit during discharge, that is when the output node is falling, is going to appear exactly like what would happen in the standard CMOS during pull down, right? The pull up is a different matter. The pull up is going to be much slower than the pull down, but the pull down is going to be of the same drive strength as that of a standard CMOS inverter. The pull up operation, on the other hand, is going to be with an effective pull up resistance of 3 times R, right? So 2/3 sized PMOS is going to have a pull up resistance of 3R, which means that this, when the output node has to be pulled up, it's going to be pulled up at a very slow rate. So if I look at the pull up logical effort, the pull up logical effort is given by 3R, which is the pull up resistance. Now the input capacitance of this gate is just going to be the input capacitance of the NMOS, because the input only goes into the NMOS, and so the capacitance is 4/3C. This is divided by the standard CMOS inverter, which is 3RC, and so you get a pull up logical effort of 4/3. The parasitic delay associated with pull up is going to be 2. If you look at the pull down the pull down is basically R into C into 4 by 3 divided by 3RC, and this is 4 by 9, right, which is close to half. So what you see is by converting from a standard CMOS to a ratioed CMOS, ratioed inverter, I'm able to get the pull down logical effort to half that of the CMOS static inverter, and the parasitic delay associated with this inverter also comes down to 2 by 3. So this circuit is going to discharge its output faster than a standard CMOS inverter. So if you look at the average logical effort of this gate, it is slightly better than the standard CMOS. It's at 8 by 9. The average parasitic delay is slightly larger, given by 4 by 3. Now the key differences you want to keep in mind between these two, again I'd like to mention, one is that there's going to be continuous leakage from VDD to ground when A is high. And secondly, when A is high, because there is going to be a competition between the PMOS and NMOS, the VOL of this transistor is not going to be 0, because when a current flows through the NMOS transistor here, there is going to be a certain VDS that needs to be supported. So this VOL is not going to be 0, it's going to be some value slightly greater than 0. Let's look at a ratioed NAND2 gate. So again, with the ratioed NAND2 gate, I have a passive PMOS load. I have a PMOS transistor connected to ground. I'll use the same logic as before, as that during discharge, I'll ensure that this stack of NMOS overpowers the PMOS. And so I size the PMOS to be 2 by 3, and I size the NMOSs in such a way that in pull down, the current is going to be 4I by 3. So now therefore, if I look up at the pull up logical effort, again each input node has an input capacitance of 8 by 3. The pull up resistance is going to be 3R, so 3R times 8 by 3C divided by 3RC, which is 8 by 3, which is again 2 times that of the static NAND2. The parasitic delay associated with the pull up transition is again slightly larger than 3. If you look at the pull down transition again has a logical effort of close to 1, which is much better than the NAND2 logical effort, and the parasitic delay associated with the pull down is going to be 10 by 9, which is again close to 1. So again here you see that the NAND2 in pull down works better in a ratioed circuit. The average logical effort is 16 by 9 and the average delay is 20 by 9. If I look at the ratioed NOR2 gate again, the NOR2 gate has a pull up logical effort of 4 by 3, pull down, or rather the parasitic delay associated with the pull up to be 10 by 3. If I look at the pull down has a good logical effort of close to half or 4 by 9, and the delay is roughly 10 by 9. So again here in this NOR2 structure, you see that the NOR2 structure has an average logical effort of less than 1, so it's less than that of a static CMOS inverter. Parasitic delay is slightly higher. So you see that the NOR structure gets much better, and the reason is because if you look at the static CMOS NOR, the static CMOS NOR had these large PMOS transistors which were sitting, right? So if you looked at our static and NOR2 structure, it had a 4 PMOS and another 4 PMOS. So this circuit is a much smaller circuit than the static CMOS, and therefore the NOR structure works better in this case. So when you're cascading pseudo-NMOS gates, you have to take care that, remember that these gates have a finite VOL. The VOL of this gate is not 0, and therefore you need to ensure that the VOL is less than the VIL. Otherwise you're not going to have a noise margin. And so here is where the noise margin gets affected. So the sizing of the PMOS and NMOS are going to affect VOL, and you need to size them up in such a way that this VOL is less than the VIL of the next stage. So these circuits, again, because of the fact that you have variation in process and because you have a lot of current flowing, because these are not circuits where one of the transistors switches off, and so therefore you have a lot of influence of variability. So one way to reduce the variability in the current is to employ current mirrors in this case, so that to ensure that this PMOS is sending a constant current of I by 3. So that can be done by using a current mirror in this fashion. Another way to reduce the static power leakage in such a circuit would be, instead of making the PMOS always on by connecting it to ground, use an enable signal on this PMOS. And again, this enable signal will need to go to ground first, then the PMOS turns on, and then you use the gate. So this way, when you're not using this gate, you can shut off the leakage in the gate by using this enable bar signal. Another logic style that was vogue and is not used anymore is the cascaded voltage switch logic. So this logic was a variation on the ratioed circuit, and it was able to achieve the speed of the ratioed logic without the static power consumption. Another advantage was it was able to provide both true and complementary outputs, but it required both true and complementary inputs. It was a very large area design. Basically, we used two large NMOS networks. So in general, if you look at ratioed gates, because of the fact that we get rid of the PMOS network, this is a largely NMOS based design with a very small PMOS which functions as the pull-up transistor. So it consists of two NMOS pull-down structures connected with PMOSs whose input and output are intertwined. So for any input combination, one of these networks is going to pull its connected node down. So for example, suppose the inputs are formed in such a way that F is shorted, so Y is pulled down, right? F bar is not shorted in that case. So when Y is pulled down, it turns on this PMOS, which pulls up Y bar to 1. And when Y bar goes to 1, this PMOS shuts off. So there is no leakage in this path because F bar network is down. There is no leakage in this path because this PMOS is turned off. And therefore this circuit looks like a static CMOS because there is no static leakage in either of these paths between VDD and ground. Obviously the gate is a much larger gate because I have to create two NMOS networks. So a simple example of creating a NAND gate would be something like this. So here you have the NAND stack. This is your standard NMOS pull down of the NAND stack. So the output here is A and B under the bar. To create the complementary network, we now create this, which consists of A bar and B bar connected in parallel. So for any input combination, one of these networks is going to be pulled down, leading to one of these outputs being pulled to 1 and the other output sent to 0. Now this CVSL logic provides great advantages, especially when you work on very specialized functions which in the CMOS implementation will consume a lot of area. For example, functions which involve a lot of XOR generally tend to like CVSL kind of implementations because XOR requires true and complement anyway. So for example, a parity generator of a 4-bit parity generator can be very simply designed using a CVSL logic just because of the fact that you have the minterm set up in such a way that sharing of inputs becomes generally hard. So in this specific case, you'll see that the CVSL gate is competitive to the CMOS gate. And generally CVSL gates tend to be fast, again because most of the logic is performed by the NMOS. The PMOS is a static load which is only going to pull up the output node in a slow fashion. Now the sizing of the PMOS in this gates become very critical because if you keep the PMOS too large, then it will slow down the falling transition because of the additional capacitance it brings to the output node. And if you keep it too small, then it would slow up the pull up of the complement. So remember, CVSL gate needs to supply both the true and complement values. So if you make the PMOS too small, the complement is going to appear at a much longer delay after the true values appeared. And because of this, generally this is very poorly suited to interface with NAND or NOR logic. It is used in special cases. Again, we'll see that mostly we don't use that in today's technologies. Now, what are the drawbacks? To recount the drawbacks of ratioed circuits, we have slow rising transitions. We have to deal with contention during the falling transition, that is the PMOS being on, the NMOS has to overpower the PMOS. We have a static power dissipation issue as well as non-zero VOL. So this is encountered, or this is, we get rid of all these issues by using a clocked circuit. That is, we used a clocked pull-up PMOS rather than a one that's always on. So the inverter in such a dynamic circuit topology is going to look something like this. You have a signal that is a clock signal, and then you have your input and the output. So in dynamic circuits, you always have two phases of circuit operation. There is what is known as a pre-charge phase when the clock is 0, and that time all the output nodes of the various gates are pre-charged to high. After pre-charge comes the evaluate phase when the clock goes high, at which point the PMOS is turned off and then signals are sent on this stage. So based when, depending if the PMOS, if the NMOS network is a pull down network, and if the pull down network gets activated, then the output node goes to 0, else the output node stays at 1. So obviously, because of the fact that there's a mostly NMOS circuits with the signals going only to the NMOS, they are fast because you have lowered the input capacitance, and also because of the fact that the clock ensures that the PMOS is not on during evaluation. There is no contention, and hence the circuit tends to be faster. Also, it has zero static power consumption. Now, the drawbacks of these kind of circuits, obviously there are quite a few, and this is the reason why they fell out of fashion except for a few applications in the SRAM. One, they require very careful clocking. Two, they consume significant dynamic power because all the gates have clocks, all the gates have capacitance, so every time you have to push the capacitances in and out. And finally, they're very sensitive to noise during the evaluate phase. So one way to fix all this is to add a clock transistor in the pull down path also, and this ensures that freak signals do not happen when the clock is high. Now to sizing, as far as sizing of these gates goes, we size the pull down such that it is similar to the smallest inverter in the technology, and the non-critical pull up we size it such that it has 2 times the resistance of that of the inverter. So for example, let's look at a footed and an unfooted inverter. So this is known as a footed inverter. This is known as an unfooted inverter because this one has a footed transistor, right? So now if I look at the sizing of these gates, the gate, an unfooted transistor sizing is going to look similar to that of the smallest inverter. Only thing, it's going to be 1 1 instead of 2 1, whereas that of a not footed inverter is going to be 1 2 2. If you look at the pull down logical efforts, which are the critical efforts in these gates, you have the pull down efforts to be 1/3 and 2/3, substantially less than the static CMOS, which is at 1, and you have the parasitic delays reduced. Now obviously, because it's a footed path, it has a longer NMOS stack. The footed circuits tend to be slower than the unfooted circuits, but they tend to be less resistant to noise. If you look at a NAND2 gate, a NAND2 gate can be implemented in an unfooted way by 2 NMOS transistors in series, a footed with 3 NMOS transistors in series. Again, here the sizing would go 1 2 and 2 as opposed to 1 3 3 in the footed case, with the pull down logical efforts being 2/3 and 1 for both cases. Again, these two are less than that of what you would get in a NAND2 gate in a static CMOS fashion. Finally, if you look at the NOR2 combination, the NOR2 combination has a pull down similar to that of the inverter, and so in a footed case also the pull down logical effort is much less. So one thing I'll draw your attention to is that the NOR2 logical efforts are very similar to the logical efforts of the inverter, right? And so that becomes an advantage in these cases. Another option which we can do in sizing is the sizing of the foot transistor can be increased relative to the input transistor, and so you can further reduce the logical effort at the input. However, this would end up loading the clock signal, and again this is possible in a few instances, but remember this clock already is a pretty sensitive signal and it's mostly in the critical path, so loading this is generally not a good idea. As I also mentioned to you previously, the logical effort of NOR gates tends to be independent of inputs in this topology. And so this gate is very well suited for wide NOR or mux-like functions because you get pretty fast circuits for those applications. Now, one particular requirement of designing dynamic gates is known as the monotonicity requirement. So if you look at this gate, when we do the pre-charge, in pre-charge, the output node is charged up to 1. And then during the evaluate phase, depending on what the input is, whether it's a 1 or 0, the output either goes to 1 or either stays at 1 or goes to 0. Now, therefore, which means that A can go from, if A goes from 0 to 1, then in that case, the output goes from 1 to 0. Now, suppose you have a case where A by mistake went from 0 to 1 but was brought down again to 0. The 1 to 0 transition during the evaluate phase at the input will mean that the output Y has to go back to 1. But because of the fact that during evaluate this PMOS is turned off, there is no way for this output node to get charged up again. Which means that in the evaluate phase, we have to have a restriction that the output can only go to high to low, which means an input has to go from low to high because this is again generally an inverting configuration. So we say that when you're designing dynamic gates, a high-low transition at the input is illegal. And secondly, what happens is you see that the input doesn't like a high-low transition, then the output is a high-low transition. So intrinsically this gate cannot be cascaded because whatever is the output of the gate cannot be an input of a subsequent gate. So that was one of the big drawbacks of the dynamic gate, and that was fixed by using what is known as a domino gate, where you take this dynamic gate and you connect a static inverter afterwards. And so therefore this high to low transition at the output at this node becomes a low to high transition at Y, and now this node can hence feed another dynamic gate. So this dynamic gate in combination with an inverter was essentially known as a domino gate. So a single clock can be used to pre-charge all the gates and evaluate all the logic gates in the chain. However, while all pre-charges tend to be parallel, evaluation tends to be sequential. Now, to make this path even better, one option would be that because again we know that this input or the output of the dynamic gate can go only from high to low, only the low to high transition of the inverter output is critical. And so basically instead of designing a static CMOS inverter, I will use a skewed gate such that I'll use a high skew gate at this inverter to favor the output rising transition so as to get a faster combination of the domino gate. Now again, the domino gate now has a different problem because we are used to static CMOS, which was an inverting configuration. We are now converting to domino gates, which are essentially a non-inverting design flow. So especially when you're designing gates such as XORs, which require both inversion, it becomes harder to design it using domino gates. So options for that would be that we push inversion if we want into static logic. We can delay the clock signal so that we give ourselves sufficient time to invert. And third rail by using what is known as dual rail domino logic. Again, we see that all these options eventually end up either increasing the area or reducing the operating frequency. And as VDD continued to scale and as noise issues become prominent, all these things became harder to control. Hence, you see the loss of usage of domino gates in recent times. The other issue with the dynamic gate was the fact that this node, which was pre-charged, has a possibility of losing charge because of leakage. Right? So the node voltage at N can drift either because of subthreshold leakage or gate or junction leakage. So either the gate leakage of the inverter or junction leakages of the drains here could end up with this charge being reduced. And so to ensure that this node, which is essentially a non-contacted node, is healthy, we sometimes use a feedback circuit with what is known as a keeper transistor, where we take the output of the domino gate and feed it to a PMOS transistor, which ensures that if this node falls low, this PMOS is eventually going to pull this node up high. So when y is equal to 0, when the output of the inverter is 0, this PMOS turns on and ensures that n is kept at high. And when n falls, the keeper, so when you want to evaluate this node, you need to design the NMOS in such a way that this NMOS needs to overpower the clock transistor as well as the keeper PMOS transistor. So technically what happens is this increases the delay of the circuit by 5 to 10%. So here again you're trading off noise margin for delay. Another style which is generally used, again which has fallen out of favor, is use of transmission gates. So transmission gates essentially consists of an NMOS and PMOS, smallest NMOS and PMOS, that are connected to in parallel with a control signal applied to the gates of each. And so based on the control signal, this path is either an open circuit or a closed circuit. If it's a short circuit, these two node voltages get identical. If not, they stay unconnected to each other. So tri-state buffers, latches, muxes, etc. can be drawn using transmission gates. For delay estimation, we assume that the unit transmission gate has a resistance R, which is that of the smallest NMOS transistor. Now normally it's very hard to find circuits purely done using transition gates only, and many TG circuits actually have CMOS connected in addition to transmission gates. So when we want to do timing or analysis of such circuits, we normally reconstruct them as CMOS circuits and then estimate delays. So an example of that would be, say we want to design a MUX using transmission gates. So a MUX using transmission gates would look something like this. And so to design or to time the circuit, I will open up the inverter, open up the transmission gates, and basically what I see is a circuit which looks like this. And so now if I want to look at the timing of the circuit, you see that this circuit looks like a CMOS circuit except for these two connections. Now these two connections actually are going to help with both the pull up and pull down, because they essentially represent the parallel paths that this transmission gate is giving. And so generally what we see is that the delay that we estimate using the CMOS configuration tends to be of the same order as that would happen in reality. In reality, the gate delay would be slightly less than what is estimated here. And that is primarily because because of this additional connections, you end up creating junctions which are of higher capacitance. The wires also introduce a certain capacitance which compensates for the increased drive strength of the structure. So essentially the delay that you get in this structure using CMOS is the same as that using transmission gates. So when we want to do timing in transmission gate circuits, it's very critical. Remember, logical effort always talks about a gate and an output. So when you're going to use logical effort or linear delay model, it is important that an input be given at the gate and then you measure the outputs. So if you look, and whereas the transmission gate, you take the input at the source drain, right? And so therefore you can't use all the techniques we've used so far for delay estimation. So the right way to solve those circuits would be to convert the circuit to a gate input one and then use analysis to calculate the delay of the gates. So to conclude, while many circuit styles exist, care must be taken when you're comparing performance across them. Circuit styles should provide sustained gain across technology scaling. This becomes important, and this is the reason why some of those older circuit styles have lost in favor. When you compare a new circuit style, it's important that you compare it to a well-characterized old technology, and therefore when you do your comparison, you make sure that you're comparing a lot of circuits, because when you compare it to a characterized old technology, one or two applications might seem faster, but when you look at the overall picture, the old technology might work out beneficial in the end. You should report and compare all delays and ensure that you have captured all the delays in all the critical paths. And do not forget clocked delays, especially if you're using clock and domino circuits. And the last part is, when you think about a new style, it's important that you think about verification, because today almost all of verification is automated. And so you need to figure out an easy and automated way to verify your design in case you're using a technology that is not static CMOS. And so with all this becoming increasingly complicated, you end up seeing most of the designs today use static CMOS or some sort of skewed static CMOS. And we see that the dynamic and domino gates are used sparingly in very specific niche areas.